This video is about complexation equilibrium. So to begin with, let's remind ourselves what a complex ion is. So a complex ion is usually a simple ion combined with or attached to, chemically bonded, to another atom or molecule that we call a ligand. So a ligand can really be anything. Oftentimes it is another ion, but it doesn't have to be. So what kind of simple ions are we talking about here? Typically these simple ions are what we call polyvalent cations. So polyvalent cation is just some metal cation that has a charge of plus n, where n is bigger than, where n is 2 or greater. So you know, a plus 2 charged cation, a plus 3 charged cation, a plus 4 charged cation, any of those tend to be polyvalent cations. And good candidates for these are transition metals, but they can also be the metals that are further down on the right-hand side of the periodic table. So the group 13 and higher metals that you see down in the lower part of the table are also good candidates for these simple ions, simple cations. So that's usually what they are. And like I said, ligands are typically other ions, but they can be other things like water molecules or carbon monoxide molecules, or even big complicated molecules like ammonia, or molecules like phenanthroline. There's a big organic molecule. So those would be complex ions. So a complexation reaction involves the formation of a complex ion. And for that reason, these are sometimes called formation reactions. So let's look at an example of a formation reaction. So this is going to be the reaction between lead. So we're going to imagine that lead can form different charge states, but we're going to imagine that this is lead 2, so lead 2 plus, and we've got an aqueous solution of lead 2 plus. And it's going to react with a ligand, and in this case the ligand is going to be iodide, so I minus, and again that's going to be aqueous. And so what we imagine is that a bond can form between the metal and the ligand, and that's going to be an equilibrium reaction, so in principle it's reversible, so that bond could break. And so we could form PBI. And so what is the charge on this complex ion going to be? We have something with a plus 2 charge combined with something with a minus 1 charge, and so that's going to give us an overall plus 1 charge. And since we started out dissolved in water and ions are very soluble in water, this is going to remain as an aqueous species dissolved in water. Okay, so this is an equilibrium, so it would have an equilibrium constant. And so we're going to call that K sub 1. So it turns out that certain metals can attach more than one ligand. And so we might want to represent a different reaction for the attachment of each ligand. So K1, the 1 here, means that we've attached the first ligand. And so how would we write this equilibrium constant? The same way we write other equilibrium constants. So products over reactants raised to the power of their stoichiometric coefficient. So PBI plus. That's the product over the reactants, so the concentration of the lead 2 plus times the concentration of the iodide, the I minus. And that would be the equilibrium constant expression for this reaction. And so we call this a stepwise formation constant. So we're getting used to equilibrium constants having different kinds of names, so we would call this kind of equilibrium constant a stepwise formation constant. So why the stepwise bit here? Well, let's look at another example. So similar example here. So we could imagine now what we do is we take the product of that first reaction and we're going to stick another iodide onto that. So we're going to start off with PBI plus, and we're going to add another I minus to that. So aqueous, that's supposed to be aqueous, equilibrium arrows. And then what are the products going to be? Now we're going to have PBI2. And we now got a plus and a minus, so they're going to cancel out to give us a 0 charge. So this complex ion is still a complex, but it's actually not an ion at all. But it still follows the rule of a simple ion combined with a ligand. So we're still going to call it a complex or complex ion. And so this is going to have a K2 for adding the second ligand on. And we would write the formation constant the same way, the stepwise formation constant the same way, products over reactants, so concentration of PBI2 over the concentration of PB2 plus times I minus, sorry, not PB2 plus. So we're going to write that the same way, products over reactants. Our reactants now are PBI plus, so we need to know the concentration of PBI plus, and we multiply that by the concentration of I minus. and that would be our K2 stepwise formation constant. We can also write a different kind of formation constant, and we call these formation constants cumulative formation constants. And they're going to be given instead of the symbol K, it's a strange convention to use the Greek letter beta. So there'd be a beta 1, beta 2, and so on for these constants. Now beta 1 is actually the same as K1, and so we're going to use K1, the stepwise formation constant, for that. So typically we don't think about the first ion being attached. But what would the beta 2 be? Let's think about that. So we would still be forming this chemical species up here, the PbI2, and so that reaction is going to be lead 2+, so we're starting out with our lead 2+. What we're going to do with the cumulative formation constant is we're going to go ahead and add both iodides in one shot. So that's the difference between cumulative and stepwise. Stepwise, we add one iodide at a time. Cumulative, we add them all at once. So they accumulate sort of all at once. And so our product is going to be PbI2 aqueous, still a complex ion, but now our equilibrium constant is different. So it's going to be this beta 2. So the second cumulative formation constant, we would call that. And again, it's going to be products over reactants. PbI2 concentration divided by the concentration of Pb2 plus times the concentration of I minus squared now because of this coefficient right here, right? All right, so that's how we write the beta 2. So it's important to notice that beta 2 does not equal the same thing as K2, so they will have different numerical values typically. I mean, maybe accidentally they would be the same, but typically they're going to have different values. All right, very good. So these are the equilibrium constant expressions, and like other equilibrium constants, we could design an experiment to measure these constants, and then once we know their values, we can put them in tables, and then we know them for then on as long as we're running the reaction under the same conditions, say standard state conditions or whatever they might happen to be. Standard conditions of temperature and pressure, I should say. So those are the two different types of equilibrium constants. And so we could continue writing them out. So there would be a beta 3, for example, which would be the third cumulative equilibrium constant. And that would be Pb2 plus reacting with 3 I minuses in equilibrium with Pb I3. And now what's the total charge? Well, we got 2 pluses and 3 minuses, so that's going to give us a -1 as the overall charge on that ion. It's still aqueous, they're still dissolved in water, and this is still a complex ion. So again, we could write out the beta 3 cumulative formation constant in the usual way with products over reactants. Notice now that our iodide concentration is raised to the third power because of the stoichiometric coefficient. And we could keep on doing this. Now, of course, there's a limit to the number of ligands that can attach themselves to a lead ion because it starts to get too crowded. And so at some point we will sort of reach the end of this chain. And to know that, you have to know that from experimental evidence or do some sort of other chemical calculation that would tell you that that molecule is no longer, or that complex ion is no longer stable. All right, so like usual, we want to be able to use equilibrium constants to do calculations to predict the equilibrium concentrations of these different ions. So let's do an example of that. Okay, so here's our practice question. So we're starting off with a saturated solution of PbI2 solid containing 0.0010 molar potassium iodide. And the important thing there is that potassium iodide is a source of the I- ion, which is what we need as a reactant in all of these complexation reactions. So we want to know what are the equilibrium concentrations of PbI plus, PbI2 aqueous, PbI3 minus, and PbI4. So we're going to use equilibrium calculations to do all of those. So here's some equilibrium constant values that we'll need. We'll need the Ksp for the dissolving of the PbI2 solid. We'll need the K1, the stepwise formation constant, and then these cumulative formation constants, beta 2, beta 3, and beta 4, for forming the PbI2, PbI3 minus, and PbI4 2 minus, respectively. Okay, so let's just draw a picture of kind of what's going on here. So here's a beaker, and this is an aqueous solution. PbI2 is kind of a nice yellow solid, so I'll draw some of that down here in the bottom. So that right there is our PbI2 solid. And up here in the solution, we've got a 0.1 molar solution of potassium iodide. So we've got K pluses and I minuses floating around in here, so that the concentration of the I minus is a concentration that we know it is fixed somehow at 0.0010 molar. All right, so that concentration we know. And then what can happen is, of course, we have an equilibrium here. That's some of the PbI2 solid. Now the KSP value is pretty small, right? So that tells us that not very much is going to dissolve when we get to equilibrium. So some of that PbI2 is going to dissolve to give us lead ions and some more I minus ions up here in solution. And then we can have the reverse of that process going on, that the Pb and the I minuses are connecting back together to reprecipitate the solid. All right, and that's represented by this equation right here, PbI2 solid in equilibrium with Pb2 plus aqueous plus 2 I minus, also aqueous. And this equilibrium is controlled by the solubility product, the KSP, for this reaction, and we know the value up here. And if we were writing that constant, it would be the equilibrium concentration of Pb2 plus times the equilibrium concentration of I minus squared. All right, so in order to work the problem, we have to go through sort of in steps and figure out what all of the equilibrium concentrations are, and then we can substitute them into our various equilibrium constant expressions, so these guys that were up here, and then compute what the unknown concentrations are. So first, we're going to start off with this sort of KSP problem. So let's think about what we know. We know the KSP value, right? And we know the I minus value because it's fixed at this number. So we can use that to solve for the unknown lead concentration. So just doing a little bit of algebra here, the equilibrium lead concentration, and there's only one equilibrium lead concentration in our solution, right? It gets controlled by this equilibrium of the lead 2 iodide dissolving. So that's going to be equal to the KSP value divided by the I minus concentration squared. And we know what those numbers are. The KSP value, 7.9 times 10 to the negative 9th, divided by 0.0010. Now that would be molar, but remember we always divide by the standard state concentration, which is 1 molar, so the units are going to cancel. And so that number gets squared right there. And we just need to plug that into our calculator to figure out what the lead ion concentration is. So I hope you're playing along with your calculator and you got the same number that I did, 0.0079 molar. Again, molarity is our standard unit, so we're going to use the molarity unit there. So now we know what the equilibrium lead concentration in this solution right here is. It's 0.0079 molar. Now what we need to do is we're going to calculate, so we want to know the concentration of PbI plus, right? All right, so what equilibrium reaction do we know that involves PbI plus? Well, that was the one that was up here, right? So this one involves the PbI plus ion, the formation of that ion. And so we're going to use that reaction. So the K1 reaction. So Pb2 plus, right? We know what that concentration is in solution, reacting with one of our I minuses to form the PbI plus ion. And so I've left out my aqueous phase labels. And again, that's going to be controlled by this K1 constant, and we know what that value is, and it's going to be the concentration of PbI plus divided by the concentration of lead, PbI2, and the concentration of I minus. So again, let's look at this expression and think about what we know. Well, we know the K1, we know the lead concentration because we just calculated it, and we know the iodide concentration. So what we need to do again is a little bit of algebra and solve for this equilibrium concentration. So PbI plus is equal to, doing the algebra here, K1 times the concentration of lead, Pb2 plus, times the concentration of I minus. Right, so that's just solving the algebra in this equation for the PbI plus concentration, and then we plug in our numbers. K1 1.0 times 10 to the second. Lead concentration 0.0079, and the I minus concentration 0.0010. And then we do the math, so go ahead and check this on your calculator to make sure you get the same answer that I do. And so I get a value of 7.9 times 10 to the negative fourth molar, right? So again, concentrations of all of these species are pretty low, so that's a pretty dilute solution, but we do have a little bit there and we can calculate it. And so for the rest of this problem, we just repeat that same kind of pattern. So looking now for the PbI2 plus aqueous ion, we use the reaction that involves the formation of that complex ion, the PbI2. And so it has a second cumulative formation constant, the beta 2 here. We write down that equilibrium constant expression. So what do we know and what do we not know? Well, we know the value of beta 2, right? So we know the value of beta 2. We know the concentration of Pb2 plus and the concentration of I minus. So again, we just do the math and solve for our unknown and plug in the concentrations. Just be careful with all of your squares and all of those kind of things to make sure you carry those along. And plug these numbers into your calculator and make sure you're getting the same value that I am. Pause this video if you want to check and hide the answer for a minute. And so this would be our final molarity. Again, since we only have two significant figures in most of these numbers, we would want to round this to two significant figures. So just 1.1 times 10 to the negative fifth would be the value correctly rounded. And then we just keep on with this procedure. So for our PbI 3 minus, same procedure. So here's our beta 3 equilibrium reaction. And again, we know the value of beta 3. We know our lead and iodide concentrations, so we solve. And this is what we get when we solve the algebra and substitute the numbers in. You might want to pause this video and just check that you get the same calculated value that I do. So rounded to two significant figures, I get 6.6 times 10 to the negative eighth molar. And last but not least, our PbI4 2 minus concentration. Same procedure. And so we write down the reaction that involves the formation of the complex ion that we're interested in. We got the beta 4 value, which we know. We still know the equilibrium lead concentration. We know the amount of iodide we have in our solution at equilibrium. And so we just do our algebra again. And so there's our equation. We just substitute our variables in there, our numbers in there, and do the calculation. So go ahead and do that on your own and check that you get the same answer that I do. Maybe pause this video and then resume to see the final answer. And there's our final molarity, 2.37. We should probably round that to 2.4 to two significant figures. And again, it's a pretty small molarity. So we'll do one extra bit to this problem just because it's kind of interesting to think about. So we want to calculate the total amount of dissolved lead. All right, so this is different than the lead 2 plus ion concentration I was talking about before, because this is now the total amount of lead that is floating around in the aqueous solution. So that lead can be combined with many different things and still be dissolved in the water, right? So first we can have free lead ions, Pb2 plus, right? And so we would need to know that concentration. But we could also have Pbi plus, so lead combined with one of the iodides. We could also have the lead combined with two of the iodides, PbI2, lead combined with three of the iodides to give us that complex ion, PbI3 minus. And finally, the lead may be maxed out combined with four iodides, I4 2 minus. So all of those are dissolved lead species, and this will tell us about the total dissolved lead. And so to get that, then we would just add up all of those concentrations that we just calculated. And all of these will have units of molarity. So you see, given the size of some of these numbers, some of these ones that are down here don't really contribute very much to the total dissolved lead. So these that are 10 to the minus 8, 10 to the minus 10th molar, they're not going to contribute so much. But adding this up, you'll see that we have more lead in this solution than we would have if we just had a saturated solution of lead iodide without the added iodide in the solution. And so when we add all this up, we get 0.0087 molar. So a little bit higher than we would have if we didn't consider the complex ion formation. So if we just thought about the common ion effect, having that I minus in the solution along with the saturated solution of lead, then we would just have a 0.0079 molar solution. But because lead can form these complex ions, we end up with a little bit more of the lead dissolving in the solution, so that the total dissolved lead, including all possible chemical species that the lead could form, assuming that this is all of them, then we would end up with 0.0087 moles per liter of dissolved lead-containing species. And so that's how we work with solubility equilibria to find equilibrium concentrations. An example that you can do yourself is to go back and work the same problem, but maybe change the I- concentration and maybe make it higher, maybe make it 0.1 molar or 1 molar, and see what happens as you change the iodide concentration to make it higher. So common ion effect would suggest that there would be less dissolved lead, but maybe as we add more I- we can form more of these complex ions, and in fact the total dissolved lead might increase. So that would be interesting to see. So that is a problem that you could try on your own. Thanks for watching.